Okay, can I start? All right. You're welcome back. And let's see. Yes. So, so this is the criteria we're going to use, and in the in the in the next part, I'm going to unpackage what concretely does this mean. In particular, I'm going to give you a criteria for what kind of n and what kind of choice of this bicharacter or Fourier short indicator, and that is implied by this condition. Okay, so we start with this condition. This criteria is what I have drawn on the board, and so I'm first going to explain what this criteria is, and then I'm going to explain these two arrows. So then we can establish the if and only if condition for the duality defect to be group theoretical. Okay, so perhaps, yeah, thank you. And so first we take P to be 1 or P to be 0. So it's just a Z 0 form, ordinary Z gauge theory. And now this is Z2 EM symmetry. And it's well known that this Z gauge theory has n² number of topological operator anyons, namely, and they are denoted by E and M, so E, electric charge and magnetic charge, and they have this obvious self-statistics. And we can also compute the mutual statistics between two different anyons. And the Lagrange subgroup of this 3D simple Z gauge theory is determined by the following three criteria. Not all of them are independent in this particular case. So first of all the anyons in the Lagrange subgroup must be bosonic. And second, any pair of the two anyons must also be have mutual trivial mutual braiding. But this is implied by the first condition. Because the mutual trivial braiding is determined by the self-statistics. And lastly, any other anyon that is not within this Lagrange subgroup must at least braid non-trivially with at least one of the anyon in the Lagrange subgroup. Okay, so one can explicitly solve these conditions and find that the Lagrange subgroup is parameterized by number p, where p is a factor of n. So namely n over p must be an integer. So the Lagrange subgroup is generated by two anyons, so p comma 0 and 0 comma n over p. And you can take arbitrary combination. So this is the Lagrange subgroup. And then we have to determine when the Lagrange subgroup is Z2 stable. So to do that, we just need to explicitly check. So starting with our Lagrange subgroup given by P, specify a parameter P, and we can consider how this EM symmetry acts on the anyons within the Lagrange subgroup. So P comma 0, this particular anyon in the Lagrange subgroup is mapped to 0 comma U times P. Remember that in the EM symmetry maps the B to U times B hat, and the B hat maps to V times B, where U and V are inverse to each other as a ZM field. And this in particular implies that so this P comma 0 anyon, which can be written as 2 pi over n times P times B, is mapped to e to the I 2 pi over n times P times U times B hat, which is just the 0 comma U times P annual. So that's what I mean on the slide. And also you can work out how the other annual are mapped under the EM symmetry. And the Z2 EM stable just means that the resulting annual must be a linear combination of the annuals within the given within the given Lagrangian subgroup. So it means that this particular annual, the EM image of the annual in the Lagrangian subgroup, must also be a linear combination of the annuals in the Lagrangian subgroup. So this is what it means. So it must be a combination of equal to x times p comma 0 plus y times 0 comma n over p. And then you can also write down the similar equation for the other annual, and just to solve these equations. Just to solve these two equations. So how to solve that? So we first consider this u times p equals to y times n over p. And this equation, of course, is valid only as a mod n number. And we can multiply both sides by p. So it means that u times p squared equals to 0 mod n. But because u and n are co-prime, so we can safely drop out this u factor. So it means that p squared divided by n must be an integer. And similarly, for the other equations, so if you look at this equality, so v times n over p equal to z times p mod n, so you can similarly derive that n over p squared must also be an integer. So combining these two conditions, you find that n must be p squared, which means that n must be perfect squared. So now we have reduced this statement to a simpler statement, which is that n must be a perfect square. And this statement is independent of the choice of this u parameter, v parameter, and also the epsilon, the Froben Schur indicator. So this statement can be is equivalent to that n is a perfect squared. Okay. So now let's prove. So now let's try to. So I have completed. I have explained what this statement means. It is just this. And then let me explain how this arrow works. So in order to establish the arrow, the upper arrow, so I'm going to first explain this upper arrow. So given n, which is a perfect squared, how can I show that the corresponding duality defect is group theoretical? So I first show that the corresponding Zn gauge theory when n is a perfect square, and after gauging the EM symmetry is a Degrad-Witten. Okay, so this is as we discussed, is equivalent to the statement that is group theoretical. Okay, so how do we show that? So first of all, we know that we have a Z2 EM stable Lagrangian subgroup, which is generated now by p comma 0 and 0 comma p, because now n is a p squared. So the two generators are these. So if we write down this Lagrangian subalgebra as these Wilson operators, then it immediately suggests that we should decompose the Zn gauge field in terms of the ZP to ZP subgauge field, because this equation is like you have a p factor in the front. So once we decompose this Zn gauge field into a ZP gauge field, two nice things happens. The first thing is that the EM exchange symmetry, which exchanges the B and the B hat, now becomes like a flavor symmetry, exchanging the A gauge field and the C gauge field. So so it only exchanges the A and the C and A hat and the C hat. And second nice thing is that when you plug in into the Lagrangian, then the original Zn gauge theory now becomes a Zp times Zp gauge theory with a Degrat-Witten twist. And nicely, this Zn gauge, Zp times Zp gauge theory has two gauge groups, Zp and Zp, and the original EM symmetry just exchanges the two Zp factors. So I hope it's now clear that under this field redefinition or its rewriting, we can see that when n is a perfect square, and the EM symmetry now becomes a flavor rotation symmetry of the Z gauge theory. Okay, so once we realize this nice property, then it's straightforward to write down the Degrat-Witten after gauging the Z2 EM symmetry. Because now gauging the Z2 EM symmetry amounts to gauging the flavor rotation symmetry of this Zp times Zp Degrat-Witten theory. So one can write down explicitly the Lagrangian of the resulting EM, the EM gauged theory. So you just use this twisted cocycle approach to write down the Lagrangian, where this Xij is the gauge field, dynamical gauge field for the Z2 EM symmetry. And then, as you can see here, you have a okay. So the first term is basically a BF term, which constrains that when you integrate the A hat, it constrains that this A must be a twisted cocycle. And the second term and last term are the Degrat-Witten twisted terms. And in particular, the last term is the choice which you can add into by gauging this Z2 EM symmetry. So this is just the twisted term corresponding to the forbidden short indicator in the duality defect. Okay, so yes.
The idea that is that when you have this special, when you solve this condition,
yes,
there's some change of variables.
Yes,
duality doesn't just acts on the electric value.
Yeah. So it just rotates between the electric field and the magnetic field separately. It does not mix between the electric and magnetic field. And this is very important that if we gauge it, we still get a Degrat-Witten theory. Yes. Yes. Sorry. So I think the logic is that only when you have, okay, maybe it's not obvious, but the statement is that only when you have a Z2 EM stable Lagrangian subgroup, then you can, then you are allowed to do this. That's right. Yes. Yeah. Oh, yeah. We haven't tried that, but when we have a non-trivial cocycle, then there is no longer a EM symmetry, right? That's right. Yeah. Sorry, I haven't thought about this problem, but it's a yeah. Yes. Yeah. Okay. So now yeah. So the resulting Degrat-Witten theory is just the theory with gauge group Zp times Zp semi-cross Z2. So it's like a non-abelian gauge theory. When p equals to 2, it's just a D8 Degrat-Witten theory. And so far we have shown that the resulting after gauging the Z2 EM symmetry, the symmetry TFT is a Degrat-Witten. But you can also find the explicit topological manipulation from the boundary point of view and show that the original duality defect becomes the ordinary like invertible defect. Okay, so far we established this upper arrow, and okay, yes. So now how about the downward arrow? And so in in 2D, we can there's a nice way to establish the downward arrow also, like physically at the physical level of rigor. So the idea is that one can simply directly do the gauging of the Z2 EM for arbitrary n. So we start with a Zn gauge theory. We gauge the Z2 EM symmetry. And of course, the resulting theory is complicated, but there's some easy piece of topological data you can easily obtain, which are the spectrum of operators and their quantum dimensions. So you start with the Z2 EM symmetry, Z2 gauge theory, Zn gauge theory, and you start with these line operators. And there is a standard procedure which tells you how the line operators change under gauging the Z2 EM symmetry. So, and the result is that in the gauged theory, you have some non-invertible lines with quantum dimension square root of n. But on the other hand, for arbitrary bosonic Daigra-Witten theory in 2+1D, all the line operators should have integer quantum dimension. So this is a well-known fact. This is essentially because the line operators are labeled by the electric charge and magnetic charge, and the electric charge is given by this conjugate cos of the gauge group, and the magnetic charge is labeled by the projective representation of the centralizer of the conjugate cos. So which Wenjie explained in her lecture. Okay, so it means that because the quantum dimension must be an integer, so n must be a perfect square. So this established the downward arrow. Okay, so collecting our results earlier and now the result here. So we are able to see that the Zn duality symmetry is group theoretical if and only if n is a perfect square. Okay, so are there any further questions?
The Z2 EM gauge theory, what are the non-invertible lines?
So there are two types of non-invertible lines. The first type is when in the Zn gauge theory, there are some lines which are exchanged on the Z2 EM symmetry. So you just in the gauge theory, you just combine these two lines and regard it as a single line. And this line has a quantum dimension too. And there is another type of line which comes from this twisted operator in the theory before gauging, and those lines have quantum dimension square root of n. So remember that in the theory before gauging, you have a EM defect. And as I mentioned before, you can consider EM. So this EM defect is a condensation of some Wilson operators, some operators in the Zn gauge theory. But you can also consider the operator which are like you can condense the operators on half of the surface. So this defines, so it's basically the EM defect supported on half of the surface. And this defines for you a twisted defect. And in the Z2 EM gauged theory, this half surface is invisible. And then you have a purely line operator. And this line operator has a quantum dimension square root of n. Yes. All the results so far on the equivalence in the 2D, right? Yes, that's right.
Yeah, sorry, it wasn't clear. I don't know if you can hear me. I think what you said so
I
far,
can
right? The
hear you.
equivalence between the perfect square condition and the group theoretical, that's
Yeah.
2D, yes?
Yes, that's in 2D, yes. Now I'm going to explain a 4D part. Yeah, okay.
So can I, just as a follow-up, I suppose
Yeah,
this
sure.
condition existed already in the math literature by Galaki and all these people, no? That n is p squared, and you can sort of have Morita equivalence to group theoretical, to like a Beck G category. Would you say that, or?
Sorry, I don't hear clearly.
Okay, let me type it in. You can answer later. Sorry.
This is known in the maths literature. Yes. Okay. Yeah. Maybe let me proceed first. Yes, the question was unsquared condition is already known in math. That's right. Yes. Yes. It's already known in the math literature. That was, yeah. I also wrote down that reference in the earlier slides. Okay. Okay, great. So now let's move on to higher dimensions. So in 4D, and we should we want to discuss a similar thing. So now it becomes the two-form gauge theory, and you have a Z4EM stable Lagrangian sub. You should search for Z4EM stable Lagrangian subgroup, and then you can. So you have a two-form gauge theory. Then if you first classify all the Lagrangian subgroup, which is generated by these two generators, and you work out the stability condition, then the condition for n is no longer a perfect square, but n is should be equal to L times m, where m is like m satisfies the following condition. So there is a integer r whose square is -1 mod m. In other words, -1 is a quadratic residue in M. There exists R. Okay. So, and again, the condition is independent of the choice of this U and V and epsilon parameters. Okay, so this is the condition. Okay, so then we have to establish these two arrows. But because I don't have time, so I'm just going to say that you can establish this arrow very concretely. So whenever n is of this type, then you can explicitly show that the Degrat-Witten is the Z4EM gauged series is a Degrat-Witten, and you can explicitly write down the Lagrangian. But the other direction is less obvious because we don't have like a notion of the quantum dimension, and we don't know what are the conditions for the Degrat-Witten. So the other side, the other condition is less obvious. But there are some consistency checks. For example, this sequence of numbers has appeared in many different literatures. For example, when n is a prime, then if you reduce to n equals to prime case, then exactly this sequence appeared in the other papers when they search for the group theoretical duality defect. And the same sequence also appeared when people studied anomalies of the duality defects. And also, interestingly, in last year, this paper showed that exactly the same sequence appeared in a seemingly completely different context, where they study the obstruction to duality preserving gapped faces. So in the last part, I'm going to explain why such a coincidence happens when because we are studying group theoretical case, and the other this paper by Anuj, Clay, and Hotat study the obstruction to duality preserving gapped faces, and why these two issues are related to each other. Yes.
I think this obstruction is what you get. So for the gap phases, I think this is the obstruction for spin manifolds.
For spin manifolds, yes, that's right.
Obstruction in the bulk, well, did the spin condition enter?
Yes. So we only focus on the spin manifold, and the reason is that when you work out the stability condition, you no longer have to work. So working at the enforcing the stability of the charge of this surface operator is not enough. There are also other subtle phases, and if you are on a non-spin manifold, then it's very difficult to work out the condition for those phases.
this thing?
Yeah, yes.
Quick
Yeah,
answer,
I don't-
because I don't know the answer.
I don't know the answer, but on a spin manifold, you can easily solve the condition for those phases, and it's exactly this condition. Okay, so let me explain the last part. So when we have the duality defect, so first of all, I'm going to focus on 4D case because the situation in 2D is a little bit different, but for simplicity, let me focus on 4D. In 4D quantum field theory, suppose it has a duality defect associated with gauging the ZN one-form symmetry, then one may ask 4 different questions regarding the duality defect. The first question is whether there is a SPT equipped with this duality defect without specifying the back character and the forbidden shore indicator. In other words, you just ask whether there is a SPT which is invariant under gauging this ZN symmetry.
Specify the by character is a nonsense question.
You can. That's right. Yeah, so you can choose. Well, the question is whether there is one choice of by character, which, yeah. And this question is essentially studied in the paper 2 years ago. Second question is whether there is a SPT equipped with the duality defect with the specified choice of the by character and the forbidden shore indicator. And this is really the definition of the anomaly of the duality symmetry associated with this given data, N, V, and epsilon. And the third question you can ask is whether there exists a TQFT, not just a SPT, with unique ground state on S3, which means that the duality defect is not spontaneously broken, equipped with the duality defect with the unspecified back character and the forbidden shore indicator. So in other words, this is again related to the fact, related to a statement that the TQFT is invariant under gauging ZN for some choice of some way of gauging the ZN. And this question has been studied in the paper by Anuj, Clay, and Hotet last year. And the last question we can ask is whether there exists a TQFT, blah, 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 with the specified choice of the back character and the forbidden shore indicator. So these are the 4 different questions. They are intimately related. And the question A and A prime are easier to study and has been studied in the literature. But the question B and the B prime are a little bit harder to study. And they will be discussed by the talk by Francesco and by Poshen next week. So please look forward to that. And so these are the 4 questions that we can ask for a given duality defect. So now let me so we have found that so there is a coincidence. So we have found this. So when in this paper, and they have found the same sequence of the number n, which coincides with the sequence when the duality defect is group theoretical. So let me explain using the symmetry TFT perspective. So we are caring about the TQFT. We are caring about the TQFT with the duality defect. So it means that suppose that we have this TQFT equipped with some duality defect. And it means that we can, so now by using symmetry TFT, we can expand this theory into a 5-dimensional slab, where on the left side, we have the dirichlet boundary condition. And on the right-hand side, we also have a topological boundary condition, which is determined by the TQFT. And then we need to ask when the TQFT is invariant under gauging the ZN one-form symmetry. As we explained in earlier part of the talk, gauging the ZN one-form symmetry just means that we in the bulk we insert a Z2 EM symmetry, Z4 EM defect in the bulk and collide with the boundary conditions. Now instead of colliding to the left-hand side, to the left boundary condition, which is the deletion boundary condition, here we collide to the right-hand side. So now the TQFT is invariant, which means that these two series are the same. Means that when you collide this EM defect to the right-hand side, the boundary condition is stable. And this is precisely, so it means that this boundary condition is stable under the Z4 EM symmetry. Translating this in terms of the Lagrangian subgroup language, it just means that this Lagrangian subgroup associated with this boundary condition of this defined by this TQFT must be Z4 EM stable. Okay, so this is precisely the condition that is required by the group theoretical duality defects, and this explains why when we study the group theoretical condition and when this paper study the obstruction to symmetric duality preserving gap phases, we encounter the same criteria. This is because in both discussions we use the condition that the ZN2 form gauge field gauge theory has a duality preserving Lagrangian subalgebra or duality preserving boundary condition. Okay, so
the idea is that you can put the AM on the right or on the left.
Yes, that's right. Yes, and so this explains why this explains why how to interpret this obstruction A prime, obstruction A prime, namely whether the TQFT is invariant under gauging ZN in terms of the symmetry TFT. Okay.
This discussion, the TQFT does not need to have unique ground state on S3.
Does not. Well, it does, because on S3 it has to be a unique ground state, but on like more general manifold like the T4 or T3, then it can be a multiple ground states. It just means, so here we are just requiring that the duality symmetry is not spontaneously broken, but the one-form symmetry can be spontaneously broken.
My question is, well, in this discussion, there is no constraint for the TQFT boundary, right? No, well.
Otherwise, you have a topological local operators. And yeah, so
A priori, there is no constraint for
yes. I think maybe you can discuss after the talk. Yeah. Okay. So now we explained we used the symmetry TFT to explain this condition for the obstruction to duality preserving gap phase A prime, and now let's further explain another interesting relation. So before doing that, let me explain the relation between these different statements. So first of all, it's easy to see that, for example, the condition A, meaning that the SPT is invariant under gauging is SPT BN one-form symmetry. This is a condition A is a special case of the condition A prime, because the SPT is a special case of TQFT. And furthermore, and the condition B is a special case of the condition A. So because the condition B means that the duality defect is anomaly free, so you have to make a specific choice. So this is for given choice of this refined data, but for A you don't have. So these relations are obvious, and on the other hand, we know that this equation, this relation is this condition is the same as the duality defect to be group theoretical. So in other words, being group theoretical is a necessary condition for the duality defect to be anomaly free. And if the duality defect is anomaly free, it must, yes. Yeah, this is the last part. This is the last slide, basically. If the duality defect is anomaly free, then it must be group theoretical. Okay, so let me just summarize here. The first statement is that the QFT with duality group theoretical duality defect is ubiquitous and is friendly to study RG flow. And second, the symmetry TFT is useful in determining when the defect is group theoretical. And lastly, is being group theoretical is related to the statement about the anomaly or the obstruction to the duality preserving gap phases. Yeah, that's it. Thank you very much.
When you say anomaly free, you
Yeah.
say that there is a fiber function. That's the definition.
Yes.
Because it's not clear to me what is a good. I mean, what is the definition of anomaly free?
Yeah. Yes, this is the definition.
Okay.
Okay, thank you very much.